Testing. Hello. What we're going to look at is review a simple sequential counter. That is, we're going to design a circuit that goes through the sequence 1, 3, 0, 2, 1, 3, 0, 2 over and over again. All right, here's a nice diagram of it. That's me on a piece of paper. It's just a loop. Where we start, where we end, doesn't matter. Nice a drawing of 1, 3, 0, 2, or 0, 2, 1, 3, or 3, 0, 2, 1. It's a ring. Both mean the same thing. We're going to construct it using a D-type flip-flop. Now remember how a D works. A D flip-flop is you have data coming in here, and the output of the future, there's a rule that says when the clock triggers, this means it's an edge, that is, it's on the way up in this case. When the edge of the clock pulse is on its way up, the input here, will be transferred to the output. So the current D of t, that means now, time now, will be in the future of time plus clock pulse over. And that's what this also means. Now, in our counter, we wanted to go, if we go back a few slides, we wanted 0, okay, it takes 1 bit. 2, I need a 1 and a 0, or a 0 and a 1, and a 1 and a 1. I need 2 bits so I can count with this many numbers. So I go here, I need 2 flip-flops. I'll call one Q0 and the other Q1. And notice both flip-flops will get a synchronous pulse, beep, and they'll both react to their respective Ds, producing some Q. So what we need to do is design some sort of circuit to feed the Qs back to here. So when the pulse comes in, depending on the current value of Q, the future Q will emerge. So here I have it. Notice I have awards in art. So I arbitrarily say 0 is 0, state 0, 1 is 1, 1, 1 is 3, and 1, 0 is 2. You can make up any meaning you want. I could make this 1, this one 2, and this one 3, and this one 0. But I'm using the actual numbers to make life easy. So when I'm in state 1, I'm going to go to 3. So that means Q1 and Q0 will be 1. When I'm in state 3, notice I go to 0. So that means Q1 and Q0 will be 0, etc. Notice how this matches the diagram, except now it's in binary. This is my present time, and this is the future when a clock pulse comes in. So now I split the thing up, because what I'm going to do is design 2 circuits. I'm going to design a circuit for Q1, and then a circuit for Q0. So you notice these are 2 truth tables. Remember how a truth table works to a K-map. A K-map is a truth table, but it's written using a gray code. Here we just go through the combination sequentially, 0, 1, 2, 3. Here I don't quite do that. This is combination 0, 0, 0, 1, which is number 1, 1, 0, which is 2. If you look over here, 1, 0 is 2. And Z is a 1, B is a 1, and A is a 1 right here. So I'm redrawing the truth table into this thing called a K-map. So here I have the now of Q1, and I'm looking at Q1, and I see Q1 is a 0, and I want it to become a 1. At what combination? At the combination 0, 1. So a combination 0, 1, I'm a 1. Then I look at combination 0, 0, and I see it has to be a 1, 1, and the other 2 are zeros. So I look at this thing and I can now simplify this K-map by saying, well, I want this to be a 1, Q0, when Q1 is a 1, excuse me, a 0, and that's it. That's all I need. So I circle them both. Q1 is a 0. So that'd be my D1. I repeat the process now for Q0. That's Q1. Here we go, Q0. I was just focusing in on this detail. These two pictures are focused in right here to show you that both of these give me this. Now I go down this row. I see combination 1, which is here, is a 1, and combination 2, which is here, is a 1. No simplification can be done here. They're diagonal to each other. So I circle both of these. There they are circled. So I have Q1 and Q0 naught right here. There's Q1 and Q0 naught. Or Q1, if you look here, Q1 is a 0. There's Q1 is a 0 going this way. And Q0 is a 1. So this combination or this combination will set D0, flip-flop 0. Now sometimes this is just me being a persnickety, the equal sign can be problematic. In the old style textbooks, people used an arrow because what does this mean? It really means you move a copy of Q1 into D1, where this is stating something of the equality of both items. So in the strict sense, I'm not an it's not quite an equality here. This is the present, and this is the present state, and this will be the future state for us. So here we have it. For flip-flop Q1, our equation was D1 is simply equal to Q1 naught. So I take the current time, put it into a NOT gate, and bring it in here. And it will follow this logic for the future. Next, Q0 says you need to look at Q1 and Q0, OR them together in this combination, and send that into D0. Here's me scratching it out with my paper and pen. Notice a terrible thing there. I might take off points on a test if you did stuff like that. I would call it ambiguous. Do you want me not to connect it? Next, here I go to Logisim, and I take some parts. I build there's my NOT gate going in. There's my AND gates and NOT gates going to an OR, going in here. And when I run this thing in the simulate mode, we didn't have to use this display. Notice I was a little tricky here. I need 4 inputs, but I turned around and put these two to 0, so it would count 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, etc., all the way up to 1, 1, 0, 0, and then back again. So I forced these two to be 0. So you would see it count 0, 1, 2, 3. Here I'm using LEDs and instead of being so fancy. And here I have the hex display being used. I do recommend building this thing, and I hope it was helpful. Obviously, please click like. Thanks.